Go to record. All right. So the end of the semester is coming pretty fast. And we have, again, 2 weeks. Next week, we finish up the course material. 2 weeks from now, we take our final exam. And let me make sure that everyone can see it here. No, yeah, so the final is going to be online, just like a web sign. So So 2 weeks from now, or 2 Wednesdays from now, you'll get an email, the final will be released. Bless you. And you'll have 2 days to complete it like a normal test. I'll put some more information about it, but more or less all the real grades are gonna be done in 2 weeks. So November 20th should be around the end date. But this week, we are finishing up chapter 6. So let's go ahead and review the announcements. We went over 6.5 on Tuesday. And please make sure to begin looking at 6.6 today. These 2 sections are in tandem with each other. So in 6.5, we study properties of logarithms. And then in 6.6, we use properties of logarithms to solve different types of algebraic equations, either equations that contain exponentials or logarithms. And generally, we call an equation that contains a logarithmic equation. Okay. And finally, we're taking the penultimate quiz this week. So this is quiz 8. And this covers sections 6.2, 6.3, and 6.4. This is going to be a normal quiz in the sense that you'll have 1 submission per question. You'll have 60 minutes to complete it. It's going to be released today around 9 o'clock, and it's due Friday at 5 p.m. So other than that, really the main ideas that we'll be looking at today will be a review of 6.2, 6.3, and 6.4. So before we look at any questions, let me go ahead and review the main ideas from these sections. In section 6.2, 6.3, and 6.4, there's 2 main equations that contain the main ideas from this section. And the first one is just the exponential equation. Y is equal to AB raised to the X. So we have restrictions on whether B can be. It can't be equal to 1, and B has to be greater than 0. And in section 6.2, we study transformations of this equation. So in other words, we're looking at how we shift the graph changes how we write this equation down. I'm not going to look at all different types of transformations, but let me just go ahead and highlight the horizontal and vertical shifts. So if we wanted to shift our graph horizontally or vertically, we rewrite our equation as y is equal to ab raised to the x minus h plus k. So here, if we had an x minus h, we'd move it to the right. If we had an x plus h, we'd move it to the left. So this is our horizontal shifts. And if we have a positive k here, we move it up. We have a negative k, we move it down. And this is going to indicate our vertical shifts. So one other important fact about these vertical shifts is that we have horizontal asymptotes associated to every exponential function. So if we shift our function up by a certain number of units, it shifts that horizontal asymptote with it. So this is going to determine our horizontal asymptote. So our horizontal asymptote is always going to be given by y is equal to k. And now the other main equation that we studied in these sections was the inverse of this equation. And the way we define the inverse is we divide both sides by a, and we get the log base b of y divided by a is equal to x. So this is slightly different than the definition in the book, but if we let a be equal to 1, in both cases, we recover the definition, so it's equivalent. And again, we have restrictions on whether b can be. B has to be larger than 1, and b is never equal to 1. Sorry, b is greater than 0. So like an exponential function, we have two types of logarithms generally. We either have increasing ones or decreasing ones. And let's go ahead and review these graphs real fast. And the way we're going to do this is we're going to do this by looking at the graph of an exponential function. So we have two cases, either b is larger than 1 or b is between 0 and 1. So when b is larger than 1, for an exponential, we have an increasing exponential. And to obtain the graph of a logarithm, we're going to flip this graph along the line y is equal to x. The graph we obtain will look something like this. Now, when b is between 0 and 1, we have a decreasing exponential. And again, to obtain the inverse function, we're going to go ahead and flip our graph across the line y is equal to x, and we'll get a decreasing logarithm. So it's going to look something like this. So one other fact about logarithms is that they have a vertical asymptote instead of a horizontal one. So this is going to be x is equal to 0. And over here, we have another horizontal asymptote at x is equal to 0. So using this graph in the definition, we can come to the following conclusions. Number one, the domain of these functions are going to be 0 to infinity, and the range is going to be all real numbers. So an important fact about the range is no matter how we apply transformations, the range is always going to be all real numbers. So this is always going to be true for every logarithm. Now the domain can change, and we'll talk about that in a second. But again, remember the vertical asymptote is given by x is equal to 0. So the way the domain changes for a logarithm function, it's going to change according to how we shift our graph horizontally. So let's suppose we shifted this logarithm over here over to the left by 5 units. So shifting it by 5, we'll get a graph that looks something like this. And what happens to the horizontal asymptote, the vertical asymptote, is it shifts along with it. So our vertical asymptote is now x is equal to a negative 5. And what this tells us is that horizontal shifts determine our vertical asymptotes. So for example, if we're given y is equal to the log base b of x plus 5, then our vertical asymptote is given by x is equal to negative 5. Okay. So this is really the main ideas from this section. And now let's go ahead and look at a few different problems. Okay. So in problem number 1, we want to go ahead and graph the function f of x is equal to a negative 6 times 8 raised to the negative x plus 3. And so let me go ahead and remind everyone basically that vertical shifts and x reflections affect each other. And horizontal shifts and y reflections change each other. And generally, again, whenever you're working with these types of transformations, you want to apply your x reflection first and then apply your vertical shift. And again, generally, but not all the time, but generally you want to apply again your horizontal shift and then your y reflection. So again, there's no ironclad rule on how to apply transformations. You just have to be careful about what you're doing with the function itself. And so this just really takes practice. Now, in this particular function here, what we do have is we have two types of reflections, and we have this vertical shift here. And what we want to do is we want to remove these transformations and get the base graph without any transformations applied to it. So what transformation do we want to take off first here? Right, yeah, so we want to get rid of this vertical shift first. So our function is going to be y is equal to a negative 6 times 8 raised to the negative x. And now it doesn't matter which reflection we take off. So we'll get rid of the 1 in front of the 6 first. So we'll get y is 6 times 8 raised to the negative x. And then finally, we'll get y is equal to 6 times 8 raised to the x. And what we're going to go ahead and do is we're going to graph these sequentially so that we can see how the transformations are working. By the time we get to number 4, we'll have our solution. So let's go ahead and draw 4 graphs real fast. Oops. Okay, so here's our 4 graphs. Let's start with number 1. We have an increasing exponential function, meaning the shape of the graph looks something like this. And we want to go ahead and keep track of our horizontal asymptote, which is y is equal to 0, and also our y-intercept. So generally, again, how do we find y-intercepts? Yeah, so you plug in, that's exactly right. We're going to plug in 0 into this equation at the x value. So evaluating number 1 at 0, we'll get y is equal to a 6 times 8 raised to the 0, which is just 6. So our y-intercepts can be 0, positive 6. Okay. So let's go ahead and look at graph number 2. And this is going to be a reflection across the y-axis, which means this becomes a decreasing exponential function. Again, we haven't changed our horizontal asymptote at all. This is still y is equal to 0. And our y-intercept is still 0, 6. So moving on to number 3, we're going to apply a reflection across the x-axis. So reflecting across the x-axis doesn't change our horizontal asymptote, but our graph is now looking like this. And so we have changed our y-intercept here. So what's the y-intercept? It's going to be 0. Yeah, so it's going to be negative 6, since all the y values are just multiplied by a negative 1. All right, and so now we're finally at graph number 4 up here, and we're just shifting our graph up by 3 units. So we can just see how this affects the horizontal asymptote and the y-intercept, the horizontal asymptote moves up to be y is equal to 3. The y-intercept becomes 0, -3. And our graph has the same basic shape. And so we get a graph that looks something like this. So number 4 is the solution to this question. Okay. So before we move on, is there any questions? Okay. Well, good. Let's keep going. And this time we want to do the opposite. We want to find an exponential equation for the following graph. And in this graph, they give us 3 pieces of information. They give us the y-intercept, which is going to be 0, 4. They give us the x-intercept, which is 1, 0. And they tell us that we have a horizontal asymptote at y is equal to 6. So we're going to go ahead and write the definition for an exponential. This is ab raised to the x. But one thing that we notice is that we do in fact have this shift up vertically by 6 units. And so we're going to alter this equation to be y is equal to ab raised to the x plus 6. Using this equation, we need to find a and b. So to find a and b, what are we going to do? Plug in the what, sorry. Right, so we want to apply, or we want to plug in the y-intercept and the x-intercept. So these are going to be conditions on what our actual function can be. So plugging in our y-intercept, we get 4 is equal to ab raised to the 0 plus 6. And plugging in our x-intercept, we'll get 0 is equal to ab raised to the first plus 6. Let's simplify this equation first, and we'll get 4 is equal to a, and b raised to the 0 is just 1. So what we're left with then is just a plus 6. This gives us that a is going to be equal to a -2. Now plug in our a value into this equation here. We'll get 0 is equal to a -2 times b plus 6. Solving for b, we'll get b is equal to 3. So we found our a value, we found our b. We just plug it back into this equation, and the solution that we're going to get is that y is equal to a -2 times 3 raised to the x plus 6. Okay. So let's keep going. In this next problem, we want to find the domain and range of the natural log of 6 divided by 7 minus x. And we can find the range pretty quickly. And this, again, follows from the fact that the range of any logarithm is always all real numbers. So we're done with the range. We want to find the domain. And this part is the tricky part. So to find the domain, we really need to go ahead and recall the following fact. What is the domain of the natural log of x? And so remember the definition of the natural log is that this is just the log base e of x. So if we want to find the domain of the natural log of x, we've already seen this slightly earlier. What values can we plug in for x to make this true? Yeah, 10, right? So we can plug in the condition that we want is these values have to be positive numbers. So the domain of the natural log of x is always going to be 0 to infinity. Another way of thinking about this is that our x values have to be greater than 0. And what that means for this equation here is that when we plug an x value into this equation, this inside piece better be larger than 0. So writing this another way, this says that 6 divided by 7 minus x is larger than 0. Solving for x, we get 6 divided by 7 is greater than x. And writing this in interval notation, this says that all the x values are going to be between negative infinity and 6 divided by 7. And so this is going to be the domain of our logarithm. Okay. Before we move on, does anyone have any questions about that? Okay. Well, let's keep going. Again, if you do have questions, you can always email me afterwards too. So let's go ahead and look at the very last question. And what we want to do is we want to find the x and y intercepts of the logarithm y is equal to the log base 2 of x minus 3 plus 1. So let's go ahead and look at the x-intercept first. And to find the x-intercept, we set y is equal to 0. So we'll get 0 is equal to the log base 2 of x minus 3 plus 1. And again, we're just going to solve for x here. So subtract a 1 on both sides, we'll get negative 1 is equal to the log base 2 of x minus 3. And we want to get rid of this logarithm here. So how do we get rid of this logarithm? Okay, so this is good. And remember that if we have an exponential, let's say y is equal to 2 raised to the x, then this is the same thing as the log base 2 of y is equal to x. So this is the definition of a logarithm. So we could rewrite our expression as the following. This is going to be 2 raised to the negative 1 is equal to x minus 3. All right. Oh yeah, sure. So maybe let me take away the numbers real fast. So let's say we had the value a is equal to b raised to the x. Now let me keep so y is equal to b raised to the x. Then maybe let's not do this by definition, but remember that the log base b of x is the inverse of this function, right? So let's apply the log base b to both sides of this equation. Then this is going to give us the log base b of y is equal to the log base b of b raised to the x. Now, this b here and this b here cancel out since this is a logarithm, and this gives us the log base b of y is equal to x. So you could think about this as a definition, or another way you could think about this is by just apply the logarithm base b of both sides and cancel this exponential out. Either way works. So in this particular problem, let's just go ahead and look at this a little further. We had this -1 is equal to the log base 2 of x minus 3. Another way to simplify this, besides using the definition, is you could raise both sides to the power of 2. So in other words, well, not both sides of the power of 2. You want these to be your exponents. So we'll have 2 raised to the -1 is equal to 2 raised to the log base 2 of x minus 3. Again, since we have a logarithm raised to the second power, or sorry, the log base 2 raised to a power whose base is 2, this again gives us 2 raised to the -1 is equal to x minus 3. So we can talk more about this after class if you want, and the videos can be posted online. But let's keep going on this problem. So going back again, we're looking for the x-intercept of this function. And now add 3 to both sides, and what we get is a 1 divided by 2 plus 3 is equal to x. So x in this case is equal to a 3.5. And so we are going to have a y-intercept, and this is going to be given by the point 3.5, comma 0. All right. So let's go ahead and look at the y-intercept real fast. So the y-intercept in this case is given by setting x is equal to 0. And our function was y is equal to, let's see, the log base 2 of x minus 3 plus 1. Right. So plugging in x is equal to 0, we'll get y is equal to the log base 2 of -3 plus 1. So real quickly, what's the domain of the log base 2 of x? Oh, so not the domain of this function here, but the domain of just the log base 2 of x. So, not quite, but remember the domain is just all the numbers that we can plug into this x value here. And again, we just want all positive x values. So this is going to be 0 to infinity. So that means that our logarithm is not defined when we plug in this -3 here. And since our logarithm is undefined, this is going to imply that there is no y-intercept. And so the solution to this particular problem does not exist. Okay. So let's go ahead and stop here. Remember, the quiz is due Friday at 5 p.m. If you do have more questions, I'll be answering emails. So go ahead and just send me any questions you have. Good luck on the quiz and have a good day and a good weekend. That's it. Yeah, so did that make sense about the whole like simplifying the logarithm?